Equity and Inclusion Action Committee is having a pasta and game night tonight. And there is a lot of pasta and pasta sauce and ramen and other things in the department office waiting for people to pick it up and participate. So I would encourage all of you to do so. It's in NEB 306 in Ashley Nelkin's office. If you're interested, there's plenty of pasta to go around. And, you know, if you want to participate in the Diversity, Equity, and Inclusion Action Committee event, there's a Zoom link on the pasta boxes. So wanted to advertise for that. NEB 306. All right. So with that out of the way, I'm going to go ahead and introduce our speaker. Dr. Xianfei Wen is a research scientist here at UT, and he works with Professor Jason Hayward. He received his bachelor's in nuclear engineering and nuclear technology from the University of South China in 2010, his master's in nuclear science and technology from Tsinghua University in Beijing in 2012, and of course Tsinghua University is one of the best universities in the world, and his PhD degree in nuclear engineering from Oregon State in 2016. So the topic of Dr. Wen's PhD work was active interrogation using the photofission technique for non-destructive assay of used nuclear fuel. He has authored 10 first author journal publications and 4 co-authored journal publications, and his current research interests include active neutron interrogation, neutron scattering instrumentation, fast timing for nuclear security and medical imaging, high-speed and high-resolution fast neutron imaging, and prompt gamma neutron activation analysis. So without further ado, I'm going to let Dr. Wen go ahead with his talk. I would also say the attendance sheet is going around, so make sure you sign the attendance sheet. I'll remind everybody at the end, too. Thank you, Dr. Wen.
Thanks for the introduction, Dr. Brown. It's my great honor to be here. My talk is about my work on fast timing measurement with fast plastic scintillators. First, I would like to give you a brief overview about the research project I have done in the past few years, including the photo-based active interrogation project I did at Oregon State, the project about radiation source detection and tracking based on fusion of radiation sensor and video sensor I did at University of Florida, and the ideas for Wen project I did at UTK here. And then I will give a little bit about the applications of fast timing, include medical imaging, nuclear security, proton therapy, and associated particle imaging. And after this, I will present you my work on the timing resolution measurement, including experiment setup, the resolution I measured with single-side readout, and the correction for the variation of depth of interaction position. At the end of this presentation, I will give you a little bit about my future work. So this project was sponsored by DOE NUP from November 2011 to November 2015. So we will work on measure the delayed gametes from photon-induced fusion of spatial nuclear materials. We did the measurement at Idaho Accelerator Center using the 25 MeV LINAC. So, but we also compared the measured delayed gamma spectra with monocolor simulations. So by process the measured delayed gamma spectra, we also determined the photofission product yield of uranium-238 and plutonium-239. So based on the ratio of 2 peaks in the measured delayed gamma spectra, we also look into the feasibility of isotopic determination. Because high rate is very challenging in photofission environment, we also worked on high resolution, high throughput gamma spectroscopy system for high rate applications. We worked on hardware and software, including FPGA and the single process algorithms. So this table shows an example of the photo feature product yet we measured for photo feature of uranium-239, and you can see from this plot just shows the example dynamic gamma spectra. We measured using HPG detectors and or NIST model spectral acquisition system. So I was the only PhD student assigned to this project, and I was the leader on all these tasks. And we produced 5 papers for this project, and I'm the first author for all of them. So this project was sponsored by DHS CWMD. It was called DNDO a few years before. So this project from October 2014 to September 2019, we worked on the main scope of work is evaluation of individual radiation sensors and video sensors. We will also build some prototype systems, and we demonstrated the performance of this prototype systems for moving source, including neutron source and gamma source. So this plot shows how we did the fusion of radiation sensor and video sensor. We also did some work on pulse shape discrimination with a click detector at very high corner rate. Because the click detector has a scintillation decay time of a few microseconds, it's very long decay. So at 375 kcps, the pulse are heavily piled up. And I did some work on algorithm development to separate or discrimination between neutrons and gammas at this high corner rate. And you can see from this plot, the neutrons and the gammas are still well separated at input corner rate of 375 kilohertz or kcps. So I was focused on the evaluation of individual radiation sensors. I started work on this project in the middle of year 2, and worked for this project for about 3 years. And I produced 4 first author journal papers and 1 co-author papers. So this project was also sponsored by DHS CWMD from September 2015 to August 2020. So we focused on a few things, including design, Wen detector, a lot of simulations about the performance of potential prototype systems. We also work on some advanced algorithms. We built some prototype systems and participated in government measurement. Dr. Hayward was also working on radiation instrumentation graduate education development. And this is one of the prototype systems we built. So you can see here, we had 3 sodium matter detectors. These detectors were read out by sensor cyclic photomultiplier. The pulse from each detector were directly sent to a K digitizer, and all the pulses were processed in real time on the FPGA of this digitizer, giving a timing information and energy information for each detected gammas. And we tested this prototype system in terms of radiation source directionality. So if 130 microcurie cesium source was stationary, and the distance between this source and the center of the detectors was about 1.7 meters, we could get a mean absolute error of about 8 degrees. And if we replace this source with a 35 microcurie source, the mean absolute error was increased to about 18 degrees. This is because the singular to loss ratio from this source is smaller compared to the stronger cesium source. So we also did some evaluation using moving source for this 130 microcurie cesium source. If we move the source at a typical walking speed and the average distance between the source and the detector center was about 5. The average was about 5 meters. So we could get a directionality of about 18 degrees if we only use the data from the radiation sensor. However, if we combine the data from the radiation sensor and the data from the video sensor, we could improve the directionality from 18 degrees to 8 degrees. So I was focused on the system development and the measurement planning execution for this project. I started working on this project in the last year of this project, and we had 3 papers from the work we did in Xianfei. So the time of flat positive emission tomography, this idea was originally developed in the 1960s. So the basic idea is, you can see from here, if we know the time of flat information about the 511 keV gamma rays, so the distribution of the 511 gammas is very narrow compared to this uniform distribution. We do not have a time of flat information. We will have this uniform distribution. And the idea was first implemented in clinical systems in 80s using barrier fluoride or cesium fluoride, and the timing resolution at the system level was only between 470 picosecond and 750 picosecond. It's not excellent. And the other reasons, it's because the barrier fluoride and the cesium fluoride have a relatively low effective atomic numbers. The system have limited sensitivities. Also, the cesium fluoride is also very hygroscopic. The barrier fluoride is also slightly hygroscopic. Another reason is the electronics for the fast timing measurement. The cost was very high. So it's just this type of flat system based on these scintillators are very hard to compete against the BGO-based non-time of flat part systems. So in the early 19th, Dr. Mencher discovered, invented the LSO or LYSO. This is a gain of change in time of flat positive emission tomography. The LSO is very faster. The decay time is about 40 nanoseconds. The density is also high. The effective atomic number is also high. So as of today, almost all the commercial time of flat part systems are being built based on the LSO scintillators. However, people are also revisiting barrier fluoride and BGO. Why? Because there are a lot of progress made in the NUV sensitive cyclic photomultipliers. That photodetector efficiency in the UV range is very high. It's compared to previous PMTs or some other photodetectors. So for BGO, there are about 10 to 20 triangular photons produced for each 511 keV gamma rays. Although the number is not very high, but the emission process is very fast. This is very beneficial to improve the timing resolution. For barrier fluoride, the cross-luminescence process could produce very fast photons. The decay time is less than 1 nanosecond. Also, the BGO and barrier fluoride are much cheaper than LSO. The price for the BGO is about half of the price of LSO. The barrier fluoride is even cheaper. It's only about $15 per cc. And there are many benefits because of the fast timing in time flat part. So because of the timing resolution of a typical time flat part system, it's less than 1 nanosecond. If we set a time window, we can remove a lot of random events. So the singular to loss ratio of the images can also be improved. So the gain of this singular to loss ratio is shown here because the diameter of the part systems and the speed of that are fixed, we cannot change that for a system already developed. But we can improve the time resolution, the coincident time resolution. If for a whole body part system, the diameter is about 40 centimeters. If the CTR is about 500 picosecond, the gain is about 2. The gain can improve to 5 if we improve the time resolution from 500 to 100 picosecond. However, if we can further increase the time resolution to 10 picosecond, we can have a gain as high as about 16. It's a very good improvement. This will give us a position resolution about the 511 keV gamma rays of about 1.5 millimeter. So this position resolution is comparable to the range uncertainty of positrons. And if we can have 10 picosecond time resolution, we can have a direct 3D information. This means we do not need to have image reconstruction, and we will have a true real-time image. And the overall benefits from the time of flight, it can reduce the dose and the image time to the patient. So there are a few commercial part systems, time of flight part systems in the market. The Siemens has the best one in terms of time resolution. It's about 240 picosecond for with half maximum at the system level. So the neutron scatter cameras, the traditional one developed by Sandia National Lab, has 2 detector planes. Each detector plane has 12 individual neutron scintillation detectors. And this camera has been used for treaty verification, nuclear safeguards, and homeland security. So it also was used to measure the neutron background at the SNS of Oak Ridge National Lab for neutrinos double beta decay. Because you can see from here, this camera is not compact at all, and the efficiency is really, really low. So the Sandia National Lab has been working on single volume-based neutron scatter camera because it much more compact, and the efficiency is also much larger than the traditional camera. So there are 2 different designs about this camera. The first one is based on monolithic scintillators. This design has 2 photodetectors read out on 2 opposite sides, and the other one is based on pixel scintillators. It has the same readout as the first design. So if you look at this plot, the separation of the first 2 neutron scattering interactions for most of the neutron events is less than 3 centimeters. And if you look at this plot, the average time difference between the first 2 neutron scattering interaction is about 2 nanoseconds. So this means we need to differentiate the neutron scattering interactions that are about 2 nanoseconds and 3 centimeters apart. And this is a very challenging problem, and the first time also has a very important rule here. So why proton therapy? Proton therapy is much more expensive than photon-based therapy. The main reason is the proton therapy can deliver less dose to the healthy tissue while focus the dose to the tumor. This could reduce the risk of secondary cancer. And the proton therapy is also a very active research topic. It involves people from biomedical engineer, medical physics, and radiology. There are many proton therapy centers in operation or being built. In fact, we have 1 proton therapy in Knoxville, Tennessee. And one of the biggest challenges for proton therapy is the in vivo range verification for quality assurance. There are a few approaches for this verification, including computer imaging, the positive emission tomography, gamma spectroscopy, and prompt gamma timing. The basic idea of the prompt gamma timing is based on measure the time difference between the radio frequency from the accelerator and the signals from the product gammas. This plot shows a very typical experiment set up for prompt gamma timing method. So there are a few very fast gamma detectors located around the target, and the RF signal and the detected signal are sent to a fast timing data acquisition system, either analog or digital. And so if you look at these two plots, the mean value of the time difference histograms has a linear relationship with the target synchronous. However, if you look at carefully, the standard deviation of this time difference histograms do not have a linear relationship with this synchronous. One of the reasons I was thinking is because the timing resolution was not good enough. If the timing resolution is good enough, there could be a linear relationship with this target synchronous. And I think the preliminary results about this approach are very promising. But I also think there are many more work to do. For example, how to deal with the bunch structure. I think this is one of the main timing uncertainty for this approach. There could be more potential project about this prompt gamma timing. I was thinking the high rate fast timing in very high radiation environment and high background for range verification. I will talk about this a little bit more on next slides. So to make this system work, we needed to optimize each component, including scintillator, photodetector, and readout electronics. So the cool adapter barrier fluoride sounds very promising to me. They are commercially available from Epic Crystal. There are two different scintillation decay components from this scintillator, one fast one and one slow one. So the first one has a decay time about 0.6 to 0.8 nanosecond, and the wavelength is between 170 to 240 nanometers. The slow one has a decay time of 620 nanosecond, and the wavelength of this slow photons is between 250 to 500 nanometers. This plot shows the emission spectra. So if we have codoppling, the slow component can be reduced or not, but the fast component are the same or identical. This means we can use this scintillator for very high rate and fast timing studies. So because the wavelength of the very fast component is in this range of 170 to 240 nanometers, we need a UV sensitive photodetectors. And recently, the FBK and Hammer-Marshall have developed some vacuum UV sensitive cyclic photomultipliers for neutrino and dark matter communities. You can see here the photo detection efficiency is relatively high. For example, it's about 24% at 180 nanometers. So there are also a few options for the fast timing ASIC-based readout electronics. For example, the Pico TDC from Sol or the time of flight part 2 from PET Systems. So in associated product image, the fast off timing is also very important. Dr. Jason Haywood and his former students have worked on this project, this topic a lot, and they had a few projects and produced many publications. For each DD reactions, one 40 MeV neutrons and one 3.5 MeV alphas are produced because the neutrons and gammas are emitted almost simultaneously and back to back. So this means if we can measure the time and the position of the alpha particles, we can know the emission time and the direction of the 40 MeV neutrons. Because we know the emission time and the direction, this is a very helpful information for many applications. I just list 3 of them. The Oak Ridge National Lab has been working on neutron transmission and induced Fisher image for a long time. Use APR neutron generator. The Lawrence Berkeley was also working on a system for determining the 3D isotopic distributions based on the inelastic scattering of 40 MeV neutrons. And the CA at France has also worked on the drug and explosive detection for a very, very long time, probably more than 20 years. And I think if we can have APR neutron generators here at the UTK, we could do some more and further work on very fast timing for alpha particles and faster neutron image. We could also do some work on active interrogation using neutrons for the detection of explosive drugs and special nuclear materials in cargo containers of different sizes. And we have been working on a DHS project about the active integration using neutrons. Probably we will hear some good news from the sponsor. If we are lucky, we will work on this topic for maybe at least 5 years, the next 5 years. So I also would like to give you a little bit about the components of a scintillator-based fast timing systems. So a typical scintillator-based fast timing system have 3 components: the scintillator, photodetector, and front-end electronics. I will just go through this one by one. So the rise time of a scintillator is related to the energy transfer process in the scintillator. It is less than 1 nanosecond. It could be tens of picoseconds or hundreds of picoseconds. The decay time could be from a couple of nanoseconds to a few milliseconds. Very fast plastic scintillators has a decay time of about 1 or 2 nanoseconds. The LSO has a decay time of about 40 nanoseconds. And for the very commonly used sodium metal detector scintillators, the decay time is about 230 nanoseconds. Clinic scintillator has a scintillation decay time of a few microseconds. Some of the scintillator glass are very slow. The decay time could be a few milliseconds. And the light yield is the number of photons produced per MeV by the energy deposition of electrons. And this is an intrinsic parameter of a scintillator. It's very different from the net output. The net output is the number of photons reaching the photodetector. So for some scintillators, they could also produce prompt photons, even for the 511 keV gamma rays. For example, the triangle photon. In BGO scintillator, there are about on average 10 to 20 triangle photons produced per 511 keV gamma rays. Although the number are not very high, but the process of the triangle emission is very fast at picosecond scale. So this is also sometimes very beneficial for fast timing. The net collection efficiency is the ratio of the numbers of photons reaching the PMD or photodetector to the total number of photons produced. It depends on the scintillator size, especially the aspect ratio, the attenuation length, and the surface parameters, for example, the roughness. It also depends on the reflector, either a specular reflector or diffuser reflector. Because the scintillation photons produced needs to travel back and forth in the scintillator many times, they could also be sprayed in the transport time. The far-field element KV gamma rays could also interact at the scintillator at different locations. We could see some variation in the depth of interaction positions. So the two commonly used photodetectors are cynic photomultiplier or PMT. So the two most important parameters about photodetectors are the photodetection efficiency and the single photon resolution for cynic photomultiplier. Their quantum efficiency or transition time spread if the photodetector is or PMT. If we're using a cynic photomultiplier as the photodetector, we also need to be careful about the correlated noise, including prompt and delayed crosstalk, as well as the afterpulse. The dark noise rate is also very important because it's very high in cynic photomultiplier than PMT. So the front-end electronics are those used to amplify the pulse from the photodetector and process this amplified pulse to get the timing and energy information for each event. So the fast timing amplifiers should have a very high bandwidth because if the bandwidth is not too high, the fast component in the pulse will be smoothed out. This information is important to the timing, but it will be lost because the gain or the bandwidth of the amplifier is not enough. The gain should also be high enough, so it is in the dynamic range of the data acquisition systems. We also want a noise level and rise time as small as possible. To process the amplified pulse, we could use either analog electronics or digital electronics or even mixed electronics. So the work I would focus on the variation of depths of interaction positions, and this work has been published in this journal. So the data acquisition I used for the timing measurement was the DRS4 digitizer from PSR. This digitizer is based on switch capacitor array. So basically, each waveform is continuously recorded in a circuit bath. And if the waveform is triggered either internally or externally, this waveform will be digitized and acquired and sent to the FPGA4 process. So there are many nice features about this digitizer. It's a really small size, similar to a cell phone, and it's very affordable. It's only $1,200 per unit, and there are 4 channels. And the sampling rate are between 0.7 gigahertz to 5.12 gigahertz, and the sampling rates can be adjusted. The ADC resolution is 12 bits. This is it's a very nice feature for the gigahertz digitizers, and the bandwidth is about 700 megahertz. The number of sample cells is 1024. This means you can have about a 200 nanosecond time window, even using a sampling rate of 5 gigahertz. So you can get the rising edge of the pulse as well as the falling edge of the pulse. So it's also feasible to have a very large fast timing data acquisition system from the DRS4 chips, because the power consumption is pretty low and the cost for each DRS4 chip is only $10. In fact, the PSI has developed a couple of thousands of channels data acquisition system based on the DRS4 chip for high energy physics. Of course, there are some advantages about this digitizer. One of them is the large data time. This is because of the ADC conversion is very slow, and the maximum trigger rate you can have is only 500 hertz. And also, this digitizer needs a very dedicated calibration. And so Another option for gigahertz sampling is oscilloscope. The problem is they are very expensive, sold of 14,000 each, and the ADC resolution is only 8 bits. So just as I mentioned, this DRS4 digitizer needs a dedicated calibration to get the base timing resolution. I will talk a little bit about how the calibrations can be done. So there are two calibrations. One is the gain calibration, and the other one is a timing calibration. The gain calibration should be done before the timing calibration. What do we need a gain calibration? Because the relationship between the ADC value and the pulse amplitude is different from cell to cell, and we need to consider this factor. So if you look at here, before the gain calibration, the noise is about 8 milliwatts, room mean square. After the calibration, it reduced to only 0.35 milliwatts. So once the gain calibration is done, we need to do the timing calibration. There are 3 steps for the timing calibration. The first step is to looking for the zero crossing segments of many free running sine waveforms, and then calculate the average amplitude of this zero crossing segments for each cell. The last step is normalization. And if you look at the this plot, so the sample rate used here was 5 gigahertz. You see the time width for each cell is not fixed. There is a distribution. This is very different from flash ADC-based digitizer. And the calibration or temperature dependent, as long as the temperature is stable, you do not need to have the calibration done again. So after the calibration, I measured the intrinsic timing resolution of this digitizer. So I measured this using a fast singular with very low noise from a waveform generator. You can see this is the pulse I used for this measurement. The purpose of this measurement just to make sure what I have measured is what I want to measure. This means the contribution from the digitizer to the total measurement timing resolution should be almost 0. So if you look at here, the time difference histogram is very symmetrical, and it's a Gaussian shape. The timing resolution for 2 channels is 2.5 picosecond standard deviation, or about 6 picosecond for with half maximum. So if I assume the 2 channels are identical, I think this is a reasonable assumption. So the timing resolution is about 1.8 picosecond standard deviation, or 4 picosecond for with half maximum. As far as I know, the base intrinsic timing resolution of analog electronics is only 3.4 picosecond standard deviation for 2 channels. This was achieved using the optical CFD, or TAC, or ADC, and ADC. So the plastic scintillator I used for my measurement was the EJ232Q plastic with a 0.5% quench. The size were 5 by 5 by 10, 12, 25, 15, 75, 100 meters. Because of the quench, the not yet rise time and the decay time are all reduced. The not yet is reduced from 8,400 to 2,900 photons per MeV. The rise time it's reduced to 110 picosecond, and the decay time, the original decay time is about 1.6 nanosecond. It is reduced to 700 picosecond after the quench. But the quench does not affect the emission spectrum. The surface of all the scintillators were well polished, and the surface were covered with ESR reflectors, except the surface read out by the photodetectors. So the photodetector I used was the 1-inch diameter Hammond Washel H6533. The single photon transistor time spread of this PMT is only 160 picosecond, 4 with half maximum. And the rise time of a single photoelectric pulse is only 700 picosecond. This is the fastest PMT I have ever known. And the PMT response is well matched with the emission spectra of the scintillators. The quantum efficiency is about 25% at the peak wavelength, which is 370 nanoseconds. So the radiation source I used was a 4 microcurrent 1322 source. The 2 511 gametes are emitted back-to-back simultaneously. Because of the relative low effective atomic number of this plastic, there is no photo peak in the pulsar distribution. So only the events with energy deposition between 340 keV and 450 keV were used to calculate the timing resolution. The 340 keV corresponded to the component age, and the 450 keV corresponded to the tail of the pulsar distribution. And all the results I will show you are expressed in terms of the 4 with half maximum. So these two plots shows the timing resolution as a function of a CFD fraction for the front irradiation and the side irradiation. So you can see from these two fingers, there is a trade-off in the CFD fraction. If the CFD fraction is too low, the timing resolution gets worse because of the large contribution from the electronic noise. If the CFD fraction is too high, the resolution also gets worse because of the random fluctuation of the arrival time of photons. And we can also see from the figures the irradiation geometry affects the timing resolution. The front irradiation gives a better timing resolution than the side irradiation. This is the case especially for the 15 millimeter non-scintillator. I also tried the leading edge discrimination method, and saw very similar trends. So this two figures shows the timing resolution as a function of scintillator length. So the timing resolution is larger when you increase the scintillator length for the front irradiation and the side irradiation. And you can also see that the front irradiation gives better timing resolution than the side irradiation. And the impact of the irradiation geometry is larger if the scintillator is longer. This non-scintillator have a higher aspect ratio. I tried the CFD and the LED time peak offs, but I reached the same conclusions. So while we're seeing this, so I will explain them a little bit in the next couple of slides. So this table shows the relative pulse amplitude of the events with energy deposition of 340 keV. The 10% to 90% pulse rise time, and the 90% to 10% pulse fall time. If we only take a look at the scintillator length, so you can see there is a large decrease in the relative pulse amplitude. You can see here. However, the 10% to 90% pulse rise time are relative comparable. This is also the case for the 90% to 10% fall time. If we only take a look at the irradiation geometry for the same scintillator, we can see that the relative pulse amplitude, the rise time, and the fall time are very comparable for both front irradiation and side irradiation. So because the optimal attenuation length of this scintillator is only about 6 centimeters, some of the photons needs to travel back and forth in the scintillator many times. And it's very likely for some of them to be absorbed before they reach the photodetector. So this is the main reason why we see an increase in the timing resolution with the increased scintillation length. So when compare the timing resolution measured on the different irradiation geometries, the main difference is about the distribution of depth of interaction positions. So if the scintillator is irradiated from the front, the distribution is exponential. If for the side irradiation, we have a uniform distribution for the depth of interaction positions. Because the uniform distribution are just wide, so this just adds some more timing uncertainty to the total measured timing resolution. This is the reason why we always see our better resolution from the front irradiation compared to the side irradiation. The question is, we know the irradiation geometry affects the timing resolution. The question is, can we correct for this effect? The answer is yes, and I will show you later. So the first approach for correcting for the variation of depth of interaction position is the mean time method. This works if we have a dual-sided readout. So if you look at these two plots, the timing resolution measured with individual PMTs increase with the scintillator length. However, if we use the average time stamp from these two PMTs, the resolution is much better, and the degradation in the timing resolution as a function of scintillator length is also much smaller. So if we use the mean time approach for the 10 millimeter non-scintillator, I could get over 79 picosecond for this half maximum timing resolution. This is the best timing resolution result I have ever measured from scintillators. And for the 100 millimeter non-scintillator, the timing resolution can be improved from 600 picosecond to 170 picosecond for this half maximum. And the 172 picosecond timing resolution is very good to me because consider the scintillator length is 100 millimeters. The aspect ratio is 20, and the attenuation length is only 6 centimeters. But the problem is in some applications, the dual-sided readout is not possible, so can we still reduce the depth of interaction variation? So I tried this approach. I call it a timing shift method. It's very similar to time walk correction, but it's more complicated because it is very easy to get the energy information for each event. It's not very straightforward to get the depth of interaction information if the scintillator is only read out by one PMT. So you can see from this table, the timing resolution measured with individual PMTs can be improved from 526 picosecond to 170 picosecond for this PMT, similar for the PMT2. And this is a very big improvement, I think. This approach can work as long as we have a depth of interaction calibration curve. So for the scintillator read out by only one PMT, we can get this information by putting some fossil on the side or the top surface of the scintillator with a scintillation decay time different from the scintillation decay time of the scintillator itself. So based on the post-shape analysis, we can get the depth of interaction position continuously. So you can see very easily about the improvement of the timing resolution by correcting for the depth of interaction variation for the single-sided readout. So I will talk about a little bit about my future work. My first future work is about the timing measurement of scintillator with a scintillator photomultiplier readout. Why scintillator photomultiplier? because they could have a very high photo detection efficiency. If you look at here, this shows the photo detection efficiency of FBK and UV samples at different over voltage. If the over voltage is high enough, we can see about 60% photo detection efficiency. This is a few times higher than the quantum efficiency of typical photo PMT. Also, the single photon multiplier could have a very good single photon time resolution. So this plot shows the total measured single photon time resolution of FBK RGB single photon multiplier of different sizes. For this 3 by 3 millimeters single photon multiplier, we could get a single photon time resolution of about 180 picosecond. This is very close to the transistor time spread of the first PMT, which is 160 picosecond. We could get even a better resolution for small size single photon multiplier. So this plot also shows the electronic noise contribution to the total measured timing resolution. If we subtract the electronics noise contribution from the total timing resolution, we got this plot. This is a very interesting one because it says the single photon time resolution of different sizes single photon multiplier are always the same. So this means the main contribution to the total timing resolution of large size single photon multiplier is from the electronic noise. And if the over voltage is high enough, for example, 10 watts, we could reach a timing resolution as good as 50 picoseconds. So another reason for the use of a single photon multiplier is over the last decades, there is a very good improvement in the dark count rate and the correlate noise, including the prompt and delayed crosstalk and the after pause. So for example, for this Hammond-Marshall single photon multiplier, the dark count rate is only 56 kilohertz per square millimeter, and the crosstalk is only 3%. Of course, there are some challenges for single photon multiplier compared to PMT. One is they have relatively small size. The typical size are 3 by 3 millimeters or 6 by 6 millimeters. Another challenge is the capacitor of single photon multiplier is significantly larger than PMT. For timing measurement, this is a problem because they just make the rising edge of the pulse look very small, and this creates some challenges for the front-end electronics. So my second future work is about the CRLB, or fundamental limits of the timing resolution of scintillator-based timing systems. So I will work on this based on some optical photo simulations. This simulation could give me the arrival time information of each detector scintillator photons. However, this fundamental limit can only be as accurate as possible as the input parameters for the simulation. The parameters include the scintillator parameters and the photodetector parameters. So I will need to measure these parameters very accurately. For example, the tens of picosecond rise time, the single photon time resolution. In fact, we have some very nice equipment for this future work. We have a picosecond pulse laser. This laser has a pulse width of 40 picosecond for width half maximum. This is a very useful equipment for measure the single photon time resolution of single photon multipliers. We have also a very nice single photon quantity detectors that it's very fast. The timing jet is only about 40 picosecond for width half maximum. So it will be used to measure the tens of picosecond rise time of scintillator as well as the nanosecond scintillation decay time. So I'm also interested in build some prototype single volume neutron scatter cameras. I was thinking about the pixelated EJ232Q and the state-of-the-art of thinning photon multipliers. Probably I will do many simulations about the potential designs. Once I have some kind of optimal design, I will build some prototype systems and test them in the lab using a California 252 neutron source. I will also evaluate the performance of these systems in terms of efficiency and spatial resolution. So I'm also interested in test these systems in a real field to see if we can locate some neutron source maybe a few meters away from the camera. So I also would like to say a little bit about this final project I will be working on, since it also involves some timing resolution measurement. So this project is about design neutron detectors for very high Counting rate neutron reflectometer at the second target station of Oak Ridge National Lab. So the purpose of this project is to address the very high Counting rate challenge. You can see from this table, the Counting rate could be 10 megahertz per square centimeter. It's a really high Counting rate. And because the second target station will have about 20 times higher peak brightness. So this second target station will create more neutrons, but it will also create more gammas. So this means we need to measure very weak signals in a strong background. The timing resolution for this project, we only need about 1 nanosecond. So consider the scintillator, the thinning photon multiplier, and the ASIC-based front readout electronics. It's not a challenge to get this timing resolution. The challenge is how can we still get this timing resolution at 10 megahertz per square centimeter. We will see if we can reach this. So here are my conclusions. The first timing is a very active topic in many important applications, including nuclear security, medical imaging, and high-energy physics. Because of the low cost and the excellent intrinsic timing resolution, the DRS4 digitizer is a very useful equipment for peak second timing resolution measurement. So the irradiation geometry also has a large impact on the timing resolution. This is the case especially for the non-scintillator. These scintillators have a high aspect ratio. So the variance, because of the variation in the depth of interaction positions, can be reduced by using the mean time method if the scintillators are read out from two sides. If the scintillator is read out from one side, we can still reduce this effect if we can know the depth of interaction calibration. Yeah, thanks. Questions?
All right, yeah, let's thank Dr. Wen. We have we have a few minutes for some questions if folks have them. So are there any questions? Also, the attendance sheet. Remember, everybody sign the attendance sheet. Where is it? Perfect. Does anybody need this? It looks like there's a number of people who haven't signed it. So let's get it signed here, and then I'll bring it over to this side of the room. Questions? All right, well, while we're waiting for somebody to come up with some questions, it looks like Alyssa's here to plug the pasta event tonight again. So, Alyssa, here.
I can't, I'm holding too many things.
All right.
All right, cool. Yeah, here's the pasta. Okay, I'm back. It's pasta day. It's pasta night. Tonight at 6 p.m., We're doing a virtual pasta night. There are going to be like our Italian professors and their families there who will totally show us how to make a good pasta. And also we're going to be playing some virtual games. So pick up your free pasta today in Ashley Nelkin's office. It's free. They have gluten-free and microwavable options. If you're like, I don't know how to cook and I just want to microwave some mac and cheese, we got you. So, and there's also sauce. Go nuts. It's in Ashley's office today, 6 p.m. on Zoom.
And there's a great QR code and a Zoom link right on the box here. So.
Yeah, that's it. Thank you.
All right, questions?
Hi. This is not on, is it? Is this on? Okay.
It's just for the online viewers, not for the room.
I was wondering if you could tell me a little bit more about your work with the wind project, the wearable IND. I didn't really understand what some of the work was based on. Yeah, it was kind of towards the beginning. So yeah, so here specifically, so you have a radiation detector that is presumably the size of an REI camping bag.
The size of the scintillator is about 2 inch by 2 inch by 6 inch.
Okay, so that's my first question. The second question is, so you've run all these tests with these radiation sources. Are you saying there when you quote the angles that you could identify the source to within that resolution, or what does that mean when you quote the angle there?
Yeah, so if you take a look at this plot, so this plot shows a comparison between the estimated direction and the ground truth. The ground truth was measured with a NADA, so it's pretty accurate. So you can see there's a good agreement between the estimation and the ground truth. This is for a moving source, a 113 microaccuracy and 137 source.
And in general, you were able to do this. It worked better with the stationary sources than the moving source, or was there no difference in the?
There are different.
Okay.
There are difference. So this is because the response we used is from the measurement with a stationary source, but we also use this response for the directionality of a moving source. There's kind of a mismatch between them. So if you look at carefully, this is why you will see a better directionality from the stationary source than the moving source. Yeah, just here you can see 8 degree, but here you see 18 degree.
When you talk about a moving source, how uniform is the motion? Like, are you just moving in a straight line relative to it, or is it moving in all sort of directions?
It's kind of a random movement at a typical walking speed of about 1.5 meters per second, and the distance, the average one is about 5 meters.
Okay, and then last question is, I assume there's some continuing work on this, so what are any planned improvements to this particular project?
Yeah, so we wanted to see if we can still track the source, if the source activity is weak. This is a challenging problem because the contribution from the noise is the background. And we also wanted to do some kind of real-time demonstration. So this we needed to put the algorithms into hardware, FPGA, or some other device.
Okay, additional questions? Any additional questions? Okay, well, if not, let's thank Dr. Wen again for his presentation. Thanks.